వచ్చే అకౌంట్కి डाटा पुरको चेका इतने सेट कर अकाउंट ఇలా రన్ చేస్తున్నాను నీకు పాసా నేను
Try to calculate quickly. You can use a calculator or whatever quickly so you can calculate it. No? Otherwise, it will take time. Question number one. Question number one. Mass of aluminium. Mass of aluminium 26, 25 grams. 25 grams. They are given you the density of aluminium 700 kilograms per meter cube. So volume of aluminium, mass over density. Mass over density. Mass is 25 grams, convert to kilograms divided by 2700. So 25 grams convert to kilograms by 2000. You'll get your answer 9.26 10 to the power minus 6 cubic meter. Okay. 9.26 10 to the power minus 6 cubic meter. Then what will be the tension if it's totally submerged in water? So full object fully submerged in water, tension means apparent weight. You all know from last week. You have done the examples. So this is your apparent weight. Huh? This is your apparent weight. Sum of forces in the upward direction balances sum of forces downward. Sum of forces in the upward direction, you can see tension plus upthrust balances weight. Tension plus upthrust balances weight. So tension plus upthrust. How do you find the upthrust? Submerged volume. This complete volume is submerged. Huh? Submerged volume 9.26 10 to the power minus 6. Density of water 1000 into G. Mass is 25 grams. Convert to kilograms into G. 25 grams convert into kilograms into G. Now simplify this. Tension plus power minus tension is 0.1574 Newton. They are asking tension, no? Right. Hope you have got this. So direct application, no? 0.1574 Newton. That's question number one. Okay. Question number two. Apply question number two. Now, when they say weight in air, mass in air means actual weight. Huh? Mass in air means actual weight. Mass in water means what? Tension. Clear. Mass in water means tension. Apparent weight. Can you see this line? I'll write above it. So I'll write here for the ones who can't see. Sum of forces upward balances sum of forces downward. Tension plus upthrust equal weight. Tension plus submerged volume. 25 10 to the power minus 3 G. Tension is equal to 0.1574 Newton. 1574 Newton. Right, no? Quickly work question number two. Number two. Right? Question number 2. Question number 2. Question number 2. Read below. Using a scale, a piece of alloy has been measured to have 86 grams in air. So true weight is given 86 grams. And 73 grams when immersed in water. What do you mean by that? Apparent weight in water. Apparent weight in water. What do you mean by apparent weight in water? Tension. That is 73 grams. Find its volume and density. If I draw a rough sketch, remember this apparent weight can be found only when it's fully submerged. Huh? Only when it's fully submerged. Right. So now basically apply sum of forces in the upward direction balances sum of forces downwards. Tension plus upthrust balances weight. Tension is 73 grams, convert to kilograms, convert to Newton. Volume here is V. Volume is V. Density of water 1000, 10 to the power 3 into G. Mass of the object, true mass, 86, 10 to the power minus 3 grams, convert to kilograms into Newton. So V, 10 to the power 4. Take this to the other side, you have 13, 10 to the power minus 3 into G. From here, you can simplify it. V is equal to 13, 10 to the power minus 6 cubic meters. What are they asking you? Volume and density. The volume is found, density of object. Mass of object divided by volume of object. The full submerged volume. Volume of object and submerged volume both are same. Mass of object is 86 grams, convert into kilogram. Volume of object 13, 10 to the power minus 6. Simplify this, you get kilogram per meter cube answer. Okay, no? So kilogram per meter cube answer 86, 10 to the power minus 3 divided by 13, 10 to the power minus 6. How much? 6,615.4. Did you all get this? Okay, no? Right. Keep working. Right, question 2 also done now. Keep working. Quickly work because you can do the MCQs all. Right. Shakti ones. Okay, no? Where are the other fellow? They are sleeping. Abral, just check and see the calculation. 0.1574 will come. Point 1574. Huh? Just check the calculation. Right. Others work, others work. Here, Shakti students, I won't do this again. Nah. So, calculations are done today. Next week, the lesson continues. Okay, look. Question number 3. Question number 3. Density of ice. Density of ice is given 917 kilograms per meter cube. Fraction of the volume above water. Now, ice will always float in water. No? Ice will always float in water. So there is a part underwater and there is a part above water. There. Now, whatever the part is underwater or submerged in water only there will be upthrust. From the total object, the weight of the object will be down. Okay. Total object, weight of the object will be down. Right. Now look at this carefully. Here, if this is balanced, sum of forces in the upward direction should balance sum of forces in the downward direction. Rule of flotation. Huh? When it's floating, that's the rule. So upward force is upthrust, downward force is weight. Now for the upthrust, what do you take? Total volume or submerged volume? Submerged. The volume under. V2. Density of the liquid, density of water. Upthrust is created by liquid. Liquid is pushing the object up. So liquid density into G. For the mass of the object, we consider the total volume. Mass is volume of ice into density of ice. That's the mass of ice. So mass of ice here, Mi, volume of ice over into density of ice into G. G cancel off. V2 rho W. What's the total volume of ice? You might confuse this. I'll write ice here. The volume of ice. Right? Total volume of ice is V1 plus V2. Whatever is below, whatever is above. V2 divided by V1 plus V2. What is this? Fraction of the submerged volume. Check and see your examples. These done. Huh? Fraction of the submerged volume. Fraction of submerged volume. What do you mean by fraction of submerged volume? Submerged volume divided by the total volume. That is equal to density of ice divided by density of water. 917 divided by 1000, 0.917. Are they asking this? No. They are asking the fraction what? Above water. Read the question. Fraction of the volume above water. So here, fraction of the volume above water. So how will you find the fraction of the volume above water? That is V1 divided by V1 plus V2. This is actually 1 minus. Total fraction is 1. 1 minus fraction submerged. Check and see. 1 minus the fraction submerged. If I cross multiply V1 plus V2 minus V2, I'll get V1. V1 divided by V1 plus V2. This answer I will get. V1 plus V2 minus V2 is V1 over V1 plus V2. So 1 minus 0.917. That's your answer. 0.083. Okay, no? How many of you got this answer? Right, okay. 0.083. Third one done. Is it clear, Shakti students? Is it clear? Sigma? Okay, no? Right. Work. Question number 4. Question number 4. Question number 4. You might, if you want, you might need some help with diagram. There is a vessel like this. The vessel is floating in water itself. There. Vessel is floating in water. They are given the base area. First question, they are asking to find the submerged height. This is question number 4. Submerged height. Then they are adding ballast. Ballast is another name for gunpowder. Imagine another weight. Part B. I am adding another weight inside. Now we have done examples like this. When you add another weight inside, they are telling this will submerge. Another weight is added inside. This will submerge how many centimeters? 30 centimeters. They are asking you what's the weight of the ballast added. That means this weight added. What is it? So don't worry what ballast is. Ballast is another name for gunpowder. So there's a block of gunpowder or gun, let's say like a bullet or whatever, like on the mass. So the vessel is floating in water. Imagine like a boat. Now I put another object inside the boat. So it will sink further. It will sink for how much? 30 centimeters. So you need to find what's the weight here added. First part, you must find the submerged height. Okay, no? So question number 4, submerged height you need to find. Part B, you must find the weight added. Okay. Right. Okay, students, any doubt put? Y is V1, 1 minus V2. No. Here we are asking fraction. Total fraction is 1. From 1, you subtract the fraction below water. Now, if you cross multiply here, V1 plus V2 minus V2 is V1 no V1 plus V2. From the total fraction, subtract the fraction submerged. Then you get the fraction above. Zara, clear? Zara, is it clear? कितनी बात? So you must find the first one is easy. So weight balancers upthrust, find H. They are given you the base area. Then after you put a weight inside, submerge is 30, they ask in this way. So when you consider upthrust, you must consider what is touching water. When you are inside the boat, is water touching you? No. Then upthrust is not acting on you. So when you are inside the boat, is water touching you? No. So upthrust is not acting on you. Boat touching the boat, thrust is acting on what? The boat. Okay, no? Carefully work. Right? Question number 4. Question number 4. A 60 kilogram rectangular box. Base dimensions 1 by 0.8. That means it's like a rectangle like this. Base dimension 1 meter by 0.8 meter. The base area is how much? Length into breadth. 0.8 meters square. So this base area here is 0.8 meters square. Right. What are they saying? The total height here is 0.5 meter. What is the depth it will submerge? So what is your theory? Total weight downwards 60 G. That's 600 Newton. What volume is touching water? This volume underneath. There will be upthrust. So sum of forces in the upward direction balances sum of forces downward. Clear? Sum of forces in the upward direction is upthrust, downward is weight. Upthrust is submerged volume. Submerged volume is this volume underwater. Underwater, how do you find the volume? Area into height. 0.8 into H. Density of water into G. That is 60 G. G cancel off. Now 0.8 H. Density of water is how much? 1000. 1060. Simplify this. H equals 60 10 to the power minus 3, 0.8. 600 divided by 8, 10 to the power minus 3. How much? 7, 5, 10 to the power minus 3 meters. 75, 10 to the power minus 3 meters. So 75 millimeter. So about 7.5 centimeters. Right. Then the next part. How much ballast should be added? How much weight should be added here? So it submerges 30 centimeters. Think, what are the forces? The weight of the boat is also there, 600 or 60 kilograms. Now the submerged volume, what is touching water? Area at the bottom here is 0.8 meters squared. Submerged volume will give you upthrust. Now be careful. Here there is a weight, m1g. When there is contact here, object is pushing the boat down. Boat is pushing the object up. Right. Mark all the forces correctly. Now, if you take the full system, R will what? Cancel. There. If you take the equilibrium of the full system, R1 will cancel. Mark the forces, but so sum of forces in the upward direction balances sum of forces downward. Upward direction only upthrust. Downward direction 60G plus the additional weight M1G. This R1 will cancel out. Clear? No? Submerged volume. Area into this height, 0.3. Density of water into G. 60G plus M1G. All the G values cancel out. How much will you get? 240 equals 60 plus M1. So what is M1? 180 kilograms. How many of you have got this answer? Okay, no? So remember, when you are inside the boat, there is no upthrust acting on you. Is water touching you? No. But is the water touching the boat? Yes. Water is touching the boat. Okay, no? Clear. So here, if I take the full system, R1 will cancel off. So upward force will be the upthrust on the boat. Downward is the weight and M1G. Okay, no? Clear. Work. That even now, no need to find pressure difference and do it, because pressure difference result and upward pressure force is upthrust. You've already shown it. So if you find the upthrust, all those pressure forces come. So you just need to mark the upthrust and work. I think we have explained this as well. Once you mark the upthrust, there is no need to find the pressure forces, right? Yeah, the weight of the ballast. Weight means mass. If you want M1G 1800 newtons, put it's okay. Right? Normally, weight we say like mass, no? That's right. If you want, put the weight and put. Right, quickly. Question number 5. Question number 5. Now, when you are doing question number 5, these are they saying. Read the question carefully. I'll give a small preview here. Foam plastic is used as a life preserver. Life preserver means what? Life jacket. life jacket. What volume of plastic must be used to keep 20% of a 80 kg man above water? There is a man now. He is wearing a life jacket. Clear? He is wearing a life jacket. 20% of the volume of the man is above water. Let's say the fellow's head is 20% above water. Right. So what's below water? So the life jacket is below water. Life preserver means life jacket. Huh? So you must think about the forces now. I won't mark it. I want you to mark. Weight of the man is there. Weight of the life jacket is there. Remember, 20% of the volume of the man above water means 80% is where? Underwater. That means, remember, there is upthrust now. When you wear a life jacket and jump into the pool or the beach or whatever, part of you is underwater. So is there upthrust acting on you? Yes. Why? Are you touching water? Yes. So there is upthrust acting on you. Is the life jacket touching water? Is the life jacket touching water? Yes. Is there upthrust on the life jacket? Yes. Normally, part of the life jacket will be outside. I didn't complicate the problem. Imagine the complete life jacket is underwater and you are floating. Clear? So the total volume of the life jacket underneath, but remember, volume of man 80% only underneath. So upthrust is acting on 80% of the volume of the man. Okay, no? Remember when you thrust, you're always on the volume where? Submerged. Not on the volume outside. Okay, no? Right. You mark the forces now carefully and work. Mark the forces now. This question number 5. I given you a small explanation. You all do the work. Mohammed, no. When you're now imagine these like you're inside a boat. If you're inside a boat, will water touch you? No. If water is not touching you, upthrust won't act on you. Simple. The weight is inside the vessel. Only the vessel is touching water, not the weight. So upthrust is not acting on that. Use the calculator and calculate. Mohammed, clear? You can see the examples done now. I have done last week example. Right. Now, who is touching water here? Man is touching water. What else? Life jacket is touching water. Man and life jacket both are touching water. That means upthrust is acting on both man and life jacket. There. If I draw this here, is wearing a life jacket. Let's say water is up to this. So what are the forces acting? Forces acting will be 80 kilogram weight. 80 G. Weight of the life jacket. mlg. Life jacket is being submerged in water. Upthrust on the life jacket. Who is underwater? Sammo. Man is underwater. So there is upthrust acting on the man. That's all. Now what? Sum of forces acting upward balances sum of forces acting downward. Upthrust on the man, upthrust on the life jacket. That is equal to weight of the man, weight of the life jacket. Weight of the life jacket. So upthrust acting on the man, upthrust acting on the life jacket. Weight of the man, weight of the life jacket. Upthrust acting on the man. First, you must find the volume of the man. Some of you all will say how to find the volume of the man. Volume of the man, you know. Mass of the man divided by density of the man. They have given you. Mass of the man is given, no? 80 kilogram. Density of the man is given 1040. So volume of the man, there you go. So volume of the man, 80% of the volume of the man. Only 80% is submerged. 80% of the volume of the man, density of water into G. Plus upthrust acting on the life jacket. So volume of the life jacket. Volume of the life jacket is fully underneath. Volume of the life jacket, density of water into G. 80 G plus. Weight of the life jacket is volume of the life jacket, density of life jacket into G. Here also you can mark. Mass of the life jacket is mass O, volume of life jacket is density of life jacket. Plus multiply. Mass of life jacket is volume of life jacket into density of life jacket. So now you can easily solve this, no? All the G's cancel off. What's your objective? Your objective is to find the volume of the life jacket or volume of the plastic. Volume of the man, you can mark carefully 80 over 1040. 80% of that. Density of water is 1000. Volume of the life jacket. Density of water 80. Volume of the life jacket, density of the life jacket. Density of the life jacket is given 580. Carefully simplify. Bring it this side. 1000 volume of the life jacket minus 580 volume of the life jacket. Whole thing take it to the other side. 80 minus 80 times 1000 divided by 1040 into 100. Don't forget to put the bracket. Here 420 volume of the life jacket. 80 here. Now 3 zeros, 1000 will cancel off. To simplify this, 6400 over 104. So what is the volume of the life jacket? This value divided by 420. If you calculate, zero 0.044 cubic meter. How many of you have got this? Good. So it's a good question, huh? Next time you jump into water, remember now. Normally, part of the life jacket will be outside. If it's outside, they must tell you how much is outside. So in this question, you must consider it's like you're pulling the life jacket down or pulling the piece of plastic down, trying to keep your head up out of water. Okay, no? Clear? No, you can't consider 1.04 as 1. Then it's density of water, no? There's a reason it's 1.04. Multiply by 1000, 1040. The density of the man is greater than the density of water. Okay. Never ever approximate 1040 to 1000. There's a reason they are given density of man is 1040 and density of water is 1000. Right. Quickly work. Question number 6. Question number 6. What have they given in question number 6? There is a scale or beaker filled with water. We have done this example. There is a reading. Now I fully submerge a metal. Here the reading is 2.3. After I fully submerge a metal, now the reading is 2.75 Newton. What are they asking? They are asking the volume of the metal. I'm sure you can do this. If you look at the examples, these given. Right, work. Quickly work. Right. Okay. Have a look. Question number 6. Last week I gave you all examples. I told you all. Why does the reading increase? Because of the upthrust. Have a look. Here there is a beaker filled with water. The reading here is 2.30 Newton. Now, when fully submerged, now the reading has become 2.75 Newton. Look at this carefully. So here you have the weight of the water and the beaker. Here reaction, equal opposite reaction. That reaction only is 2.3. Here you have weight of the water and the beaker. Here there is upthrust. Here there is tension. Here there is weight of the object. If there is upthrust, there is also what? Downthrust. Downthrust is there. Downthrust is there. Here, beaker is pushing the scale down. Scale is pushing the beaker up. Okay. Now we consider the forces acting on the beaker. We consider the forces acting on the beaker. Sum of forces in the upward direction balances sum of forces downward. If you want here also you can apply. Sum of forces upward balances sum of forces downward. These on the beaker and water. Upward you have R1, downward you have weight. Weight of beaker and water. What is your reaction? Reaction is 2.3 Newton. So weight of water and beaker is 2.3 Newton. You can use it here. So on the beaker and water. On the beaker and water. This is on the object. On the beaker and water you have reaction R2. Downwards you have down thrust plus weight of water and beaker. What is your reading? 2.75. Weight of water and beaker 2.30. 0.45 is your upthrust. Remember, down thrust and upthrust both are equal. What are they asking you? They are asking you volume of the metal. Volume of the metal is submerged volume density of water into G. 0.45 Density of water is 1000 into G. 1000 into G. Volume 0.45 10 to the power minus 4 cubic meters. Simplified 4.5 10 to the power minus 5 cubic meters. There you go. Volume of the metal. How many of you have got this? Right now. Okay. Next one. Question number 7. Now, question number 7, what are they asking you? This was we have done example. Inside a metal, there is a hollow part. Volume of hollow, volume of metal. For the weight of the object, volume of the metal is important. For the upthrust, the complete volume is what? Important. Example, plastic ball. If you take the weight of a plastic ball, what's important? Volume of plastic into density of plastic. Do you consider the empty volume inside? But if you submerge a plastic ball underwater, you consider the full volume. Volume of plastic and volume of air. Okay, no? So that concept you have to use to get this answer. Anybody still writing this? Shakti students? Anybody still writing the one on the board? I'll quickly write. Others quickly work. You can keep working. Huh? 7, 8, 9, 10, 11, 12. Keep working. Now here reaction balances the weight. No? So this reading is the weight of the beaker and water. Okay. Now the weight of the water and beaker has not changed, but I have fully submerged the metal. Now on the metal, there is the weight of the metal, there is upthrust, there is tension. Liquid is pushing the object up, upthrust. Object is pushing the liquid down, what do you call it? Downthrust. If you consider the water and the beaker, weight of the water and the beaker is there, downthrust is there, then there is reaction. This is not touching the beaker. So you can't take this weight. If the object was touching the bottom, yes, that weight will come. This is not touching the bottom, so you have downthrust and you have reaction here. So reaction R2 upwards, downthrust, weight. New reading is 2.75. Reading is the reaction, 2.75. Weight of the water and beaker there, 2.3. Then you can find the downthrust. Downthrust and upthrust both are what? Okay. There. So you need to understand that here on the object there is upthrust. Liquid is or water is pushing the object up. Object is pushing the water down. Downthrust. Newton's third law of force. Is it clear? Newton's third law of force. From there you can find the weight of the metal. Clear? SPGR means specific gravity. Specific gravity is relative density. Units and dimensions knowledge. Okay. SPGR, specific gravity. Specific gravity is equal to relative density. Okay, now? Right. Look at question number 7. Question number 7. Pure gold is suspected to have a hollow center. It has a mass 38.25. Mass of gold. Mass of gold 38.25 grams. 36.22 in water. Apparent weight in water. Or apparent mass in water. Apparent mass in water 36.22 grams. That's your tension. What are they asking you? What's the volume of the hole? Think carefully and answer. If this is your metal, this is your hole inside. Volume of the hole, volume of the metal. For the mass, what is important? Volume of the hole or volume of the metal? Volume of the metal. Here nothing, no? Hole volume, nothing. So mass of the metal is volume of the metal into density of the metal. Mass of the metal is 38.25 grams. Convert to kilograms. Density of the metal, you can do this in the same units, but I'll use it SI units, otherwise. There you go. The volume of the metal is going to be in cubic meter, you can find. In cubic meter, you can find. 38.25 10 to the power minus 3 divided by 19,300. 1.98 10 to the power minus 6 cubic meter. Right now. Then I fully submerge this in water. Tension only is given. Apparent weight 36.22 grams. Convert to kilograms into G. Weight 38.25 grams. Convert into kilograms into G. Volume of the metal, volume of the hollow, there will be upthrust. Remember, upthrust will act on the total volume. So sum of forces in the upward direction balances sum of forces in the downward direction. Upward direction, you have upthrust and tension. Downward direction, you have the weight. 38.25 grams, convert into kilograms into G. What is upthrust? Submerged volume. Whole volume is underneath. Volume of the metal plus volume of the hole. Density of water into G. Plus tension. 36.22 grams, convert into kilograms into G. We can erase this now. There you go. That is equal to 38.25 10 to the power minus 3 G. Take this to the other side. Volume of the metal plus volume of the hole. Let's cancel all the G's off. 36.25. Sorry. 38.25 minus 36.22. 2.03 10 to the power minus 3. Volume of the metal, volume of the hole. Take this to the other side. 2.03 10 to the power minus 6. What is volume of the metal? Already found. 1.98 10 to the power minus 6. Volume of the hole you can find. Take it to the other side. Volume of the hole is 2.03 10 to the power minus 6. 1.98 10 to the power minus 6. 2.03 minus 1.98, 0.05 10 to the power minus 6 cubic meters. That's 5 10 to the power minus 8 cubic meters. Volume of the hole. Anybody you got this? Right. So again, this we have done another example. For the weight of the object, the volume of the metal will come. The upthrust, volume of metal and volume of hole both will come. That is one sentence there. In these type of problems, when we consider the weight of the object, when we consider the mass of the object, when we consider the mass of the object, we must consider the volume of the metallic part. We must consider the volume of the metallic part. We must consider the volume of the metal part or metallic part. And when we consider the upthrust, when we consider the upthrust, we must consider the total volume. We must consider the total volume. So volume of metal plus volume of hole. When we consider the upthrust, we must consider the total volume. When we consider the upthrust, we must consider the total volume, which is the volume of the metal and the volume of the hole. Which is the volume of the metal and the volume of the hole. Right. I'm sure some of you all have finished question 8 also. I'll do that. There is a cube. Cube means all the sides are equal. 2 centimeter each. Right. Appears to have a mass 47.3. Appears to have a mass means apparent weight. Right. So I fully submerge this in water. Tension in water is given. Tension in water is 47.3 grams, convert into kilograms into G. Weight of the object is the same. Upthrust in water is there. So I can apply sum of forces upward, balances sum of forces downward. Sum of forces upward, tension plus upthrust, balances weight. Tension here is going to be 47.3 10 to the power minus 3 G. Upthrust is how much? What's the volume? 2 times 2 times 2, 8. 8 cubic centimeter convert to cubic meter, density of water into G. That is mg, equation number 1. Equation number 1. Now I fully submerge the cube in a different liquid. Different liquid. What's the liquid? Glycerine. Weight of the object will not change. Upthrust, of course, will change because density changes. They are asking you, what will the mass appear? That means apparent weight in liquid. Sum of forces upward, balances sum of forces downward. Tension in the liquid plus upthrust in the liquid equal weight. Tension in the liquid plus upthrust is 8 cubic centimeters convert to cubic meters. Density of glycerine 1.26 into 1000, 1260 G. That is mg, equation 2. What can you say about equation 1 and 2? Both are equal to the weight. Both are equal to the weight. If both are equal to the weight, you can say equation 1 equals equation 2. So 47.3 10 to the power minus 3G. 8 10 to the power minus 6 rho WG. TL 8 10 to the power minus 6 1260 G. all the, okay, don't keep the G value without cutting it. Now find tension. Find tension in Newton. So 47.3 10 to the power plus 8 10 to the power minus 6 into 10 to the power 4. G is 10, no? Minus 8 10 to the power 1000 to 60 into 10. You will get 0.4522 Newton. So how do you convert to grams? 45.22 grams. That's your apparent weight in glycerin. You can keep in Newton also if you want. Apparent weight in glycerin. How many of you have got this one? Okay, now we are doing. No need, no down thrust. There is no Beaker question. Here we are applying on the object. On the object only up thrust. If the beaker comes only down thrust. Clear? Sifa? Is it clear? If the beaker comes, yes, down thrust. But if the object comes, it's only up thrust. Okay. Right. Question number 9. You all do it. A balloon and a gondola. What do you mean by the gondola? The place where people stand and go. In a hot air balloon. I'll taste this part till we are done and finished. Now in a hot air balloon, you have the balloon and the place where people sit and go. This part have you all seen? Around the world in 80 days, cartoon. Yeah. This place here is the gondola. That is where the weight is acting. So here, don't forget, surrounding is air, inside helium. So helium will have a weight. Also, the balloon is in air. So this is the liquid. There is upthrust. And then there's a weight. Carefully work. They're asking how much weight should be put inside, how much weight should be put inside. So this travels upwards. So that means it's traveling with a maximum velocity. Maximum velocity means acceleration is how much? 0. So find the weight that should be added for the balloon to travel with a constant speed. Make a small correction there. Helium density is 0.183 kilogram per meter cube. Not kilometer per meter cube. There is no kilometer, no. Kilogram per meter cube. Right work. Question number 9. 9, 10, 11. Well, easy. Yeah? Quickly work. Specific gravity is relative density. Right now? Okay. Right. We'll work question 9 and 10, then have a break. Question 9. A balloon and a gondola. Balloon and a gondola have an empty mass of 200 kilograms. That's 200 G. Balloon contains 900 cubic meters of helium. So helium weight is also there. This balloon is submerged in air. Submerged in air, there is upthrust also acting. What are they saying? Find the added weight. Find the added weight here. So the balloon can lift off. The acceleration 0. Simplify this. Upward forces, balancers, downward forces. Upthrust, balancers, weight of helium, weight of the gondola, plus weight of the added mass. Weight of the added mass, weight of the gondola, weight of the helium balloon. What is upthrust? Submerged volume. They have not given this volume, so neglect that. This volume here, 900. What's it submerged in air? Density of air into G. Mass of helium is volume of helium. If you want, write on the side. Volume of helium into density of helium. Mass of helium is volume of helium into density of helium. 200 G plus M1 G. All the G cancel off. 900 density of air 1.29. Volume of helium 900. Density of helium 0.183. 200 plus M1. Carefully simplify, you can get the M1 value. M1 value. So 900 that minus 200. 796.3 kilogram. Did you all get this answer? People who got this? Right. Question number 10. Question number 10. A spring whose composition is not clearly known. Spring means you all know. No? The spring has a volume. Huh? There is a volume here. It can be either bronze or brass. Either one of the two metals. Your job is to find the density of the metal. When measured in air, the weight is given. True weight is given. 1.26 grams convert to kilograms into G. Apparent weight in water is given. That means tension is given. 1.11 grams convert to kilograms into G. And then here, don't forget there is upthrust. So you can apply. Sum of forces in the upward direction balances. Sum of forces in the downward direction. Upward direction, tension plus upthrust, balances weight. Tension is 1.11, 10 to the power minus 6. Now be careful. For upthrust, what is touching water? The volume of water, metal touching water. Vm, volume of metal. Vm is volume of metal. Volume of metal. Density of water into G. 1.26, 10 to the power minus 3 G. All the G values cancel out. Simplify this carefully. 1.26, 10 to the power minus 3 minus 1.11, 10 to the power minus 3. divided by 1000. There you will get volume of the metal. Volume of the metal is 1.5 10 to the power minus 7. That's not the objective. But once you know the volume of the metal, you can make a small connection. Mass of the metal is volume of metal, density of metal. For the weight, the volume only is important. Mass of the metal is here 1.26 10 to the power minus 3 kilogram. Volume of the metal is 1.5 10 to the power minus 7 density of the metal. Density of the metal you can find 1.26 10 to the power minus 3 divided by 1.5 10 to the power minus 7. You will get 8,400 kilograms per meter cube. Now look at the question. What is 8,400 density? Bronze or brass? That's the density of brass. Therefore, the metal is brass. Therefore, the metal is brass. Right? Also, we can do question number 11. That's a very simple question. I'll do it here itself. What fraction of volume will be submerged? Quartz is floating in mercury. This is like the earlier question, question number 2. Sorry, question number 3. Above you have V2, below you have V1. Weight balancers upthrust. Don't forget the liquid is mercury now, not water. So sum of forces in the upward direction balances. Sum of forces downward. Upthrust balances weight. What is upthrust? Submerged volume. Density of mercury Hg into G. What is the mass? Total volume. V1 plus V2. Density of quartz into G. G cancel off. What are they asking you? Fraction submerged. V1 divided by V1 plus V2. That is density of quartz over density of mercury. Quartz density 2650. Mercury density 13,600. Get the ratio. 2650 divided by 13,600. The fraction is 0.195. I'm sure all of you all will get it. Clear? I'm sure all of you all will get this. Okay, no? On the board, we have question 9, we have question 10, we have question 11. Right, have a break and come. After the break, we do question number 12 and then the MCQs. Right, have a break and come. Right. Read question number 12, will you? Enough time to work. Question number 12. A glass of water has 10 cubic centimeters of ice floating in it. 10 cubic centimeters of ice. The glass is filled up to the brim with cold water. Glass is filled up to the brim with cold water. Right. Now remember, there is a volume on top, there is a volume at the bottom. Total volume is going to be 10 cubic centimeters. Right. By the time the ice has completely melted, when the ice completely melts, how much water would have flowed out? Right. Good question. Now, some of you all will think, okay, when this melts, water is added, there will be overflowing. Let's look at this carefully. Yeah? First here, it's floating. Weight balances upthrust. Sum of forces in the upward direction balances sum of forces in the downward direction. Upthrust balances weight. Upthrust, submerged volume. Density of water into G. Mass of ice. Mass of ice is volume of ice. 10 cubic centimeters convert to cubic meters. Density of ice 920 into G. Look at the board carefully now. Submerged volume is 920 10 to the power minus 8. Simplify this. 9.2 10 to the power minus 6 cubic meters. So submerged volume is so much. Now think carefully logically. When the ice block melts, what happens? Mass of ice will convert into mass of water. The volume will be different, but the mass converted will always be what? Same. So the mass of ice converts to mass of water. Mass of water. There. So what is the mass of ice? So mass of ice from here you can find volume of ice into density of ice. That's the mass of water. Mass of water added after melting. Mass of water added after melting. So your answer here will be 9.2 10 to the power minus 3 kilograms. Mass of water added. Right. Now what are we interested? Volume of water added. Because if the volume of water added is greater than this volume, now this bottom volume is the submerged volume. Now, if the volume added is more than this volume, that will overflow. Is it clear? The space in the bottom is taken by ice. When this completely melts and adds, if the volume added is more than this space, it will overflow. The volume of water added, that's mass of water 9.2 10 to the power minus 3 into density of water. That's going to be 9.2 10 to the power minus 6 cubic meters. Interesting. The submerged volume here and the volume added both are what? Same. That means the level does not change. Overflowing takes place. It's a very important MCQ. When an ice is floating and ice cube completely melts, there is no overflowing taking place. Level of water does not change. Again, look now. Here, if you look, this is your submerged volume part. Ice melts. If it adds into this volume, this space is now disappearing. No, ice is melting. No, this space is disappearing. If the volume added is more than this, it will overflow. If the volume added is equal to this, level does not change. I have shown the mass volume of water added is same as the submerged volume. So what will happen? Level does not change. No overflowing takes place. Is it clear? So when the ice cube melts, this will disappear. No? For that space, water is added. For that space, water is added. For this space, water is added. Now water added is water added is also 9.2 10 to the power minus 6, which is same as the submerged volume. So will there be any overflowing taking place? No. No overflowing taking right there. How many got this answer? 1%. Good. Other side. That side. As shown in the calculation, we can find the submerged volume. We can find the submerged volume. As shown in the calculation, we can find the submerged volume. We can find the submerged volume. When the ice cube melts, when the ice cube melts, when the ice cube melts, the same mass of ice is converted into mass of water. The same mass of ice is converted into mass of water. Same mass of ice is converted into mass of water. And we can show that the volume added and we can show that the volume added we can show that the volume added is same as the submerged volume. Is same as the submerged volume. Volume added is same as the submerged volume. Therefore, no water will overflow. Therefore, no water will overflow. No water will overflow. So when the ice cube completely melts, level of water does not change. Ice cube completely melts, level of water does not change. Level of water does not change. Okay, no? So this is a very powerful basic question. Complete volume here again, look at the complete volume 10 cubic centimeter. You can find the submerged volume. So this volume only is this place. This space only is taken by ice. Now, once it melts, complete mass of ice converts to water. That water is going to be added in this space. Why that space only is disappearing. Here, water is slowly filling in. When ice is melting, water is slowly filling in. Clear? Water is slowly from all sides filling in. But the problem is, water added due to melting, I have found. That volume and this volume both are same. So they might ask you another question. Ice will melt and fall there. So there is no movement, no transfer. From outside, there is no transfer. Whatever is melting is collecting here. Why is this happening? Mass is volume into density. You know? Mass is same. But remember, density of water is high. So volume of water is what? Less. Clear? Volume of ice is 10. Density of ice is small. Volume of ice is large. Larger ice volume will become what? Small amount of water. Is it clear? Larger ice volume will become what? Small amount of. Okay. No? So that water only is added to this space. So what happens? No overflowing takes. Clear? Okay. Very important logic-based question. Huh? Very important logic-based question. Okay. Right. You're finished. Write this down. Page 31, question number 16. Page 31, question number 16. Students, I have put it in your group. Right, again, look. Now, some of you are thinking, what's happening here? We are taking this whole volume. Whole volume is there in this mass. Here. Whole volume is taken. That's in the mass. That mass only converts to water. Volume of water is so much. That volume and submerged volume both are what? Same. That volume is what? Coming into that smaller space. So level does not change. Page 31, question 16. Page 31, question number 16. Quickly work. Right. Okay, look. Question number 16. Hydraulic braking system is given. Hydraulic braking system is given. Here you have a pedal. Here there is a master cylinder. Cross-section area reduces slightly. Here you have the brake pad. Secondary cylinder. Secondary cylinder. Here you go. Right now. Here you have the wheel. Wheel is rotating. Right. Master piston area 1 centimeter squared. Secondary piston area 3 centimeters squared. To the pivot point here 5 centimeters. Here 20 centimeters. And we are applying a force. Okay, now read below. Figure shows a hydraulic braking system which will be used to stop a rotating wheel. A force F is applied perpendicular to the pedal. Pedal rotates freely around the axis passing through point A. Axis passing through point A. Right. The resulting pressure is transmitted through brake fluid to identical pistons P2. The brake pads L, these are the brake pads. Brake pads L attached to the pistons move a little distance. Assume the brake fluid is incompressible, areas are given. Right. Roman number 1. When a certain force is applied, the master piston moves 0.6 meters. How far does a single brake pad? Keyword single. So volume displaced here and volume displaced by both the pistons should be what? Same. So volume displaced by master piston equals 2 times volume displaced by brake piston. Area is 1 centimeter squared. Displaced distance 0.6. Area is 3 centimeter square, distance x. 0.6 centimeter cube divided by 6 centimeter square. Your answer is 0.6 centimeters. 0.1 centimeter. Each brake pad will move 0.1 centimeter. How many of you got this answer? Right. Okay. Others may be careless mistake. Roman 2. F is equal to 10 Newton. What is the applied force on piston P1? So piston P1, how do you find the force? When I move this here, piston is pushing the liquid. Liquid is pushing the piston in the opposite direction. Piston is pushing the liquid. Liquid is pushing the piston. Take moments about A. Clockwise moments equal anti-clockwise moments. Clockwise moments, F1 into 5 centimeter. Anti-clockwise moments, 10 times 20. F1 equals 40 Newton. Force on the master piston. How many people got this? Part A, part B. Calculate the pressure on the master piston. Pressure is force divided by area. Force 40, area 1 centimeter squared, convert to meter squared. 4 10 to the power 5 Pascal. What do you know from Pascal's principle? Fully enclosed fluid, pressure is equally transmitted. Pressure is equally transmitted everywhere to the container and to the liquid. Okay, no? There you go. Part C. Calculate the pressure on the brake pads due to the pressure exerted. So pressure will be the same, 4 10 to the power 5. According to Pascal's principle. If the coefficient of, you'll find the force. Pressure equals force divided by area. 4 10 to the power 5. Area is 3 centimeter squared, convert to meter squared. F2 is equal to 120 Newton. How many of you got this? Part D. Part D. Look at this picture now. From both sides, the brake pads come. If the coefficient of dynamic friction is 0.5, what's the friction force? Look at the board carefully. The brake pad is touching here and on the other side as well. So what is your normal force? The rotating this way, what's your normal force? Normal force is the force acting here, F2. Understood? F2 only is pushing on the wheel. So normal reaction is equal to F2. So wheel is rotating in that direction. Friction will act in the opposite direction. That will create a frictional torque. Understood? Here, how many frictions are there? From front, there is a brake pad. Behind also, there is a brake pad. Don't forget. So how many frictions? 2 frictions. So when the wheel is rotating this way, you are touching it this way and that way, like this. So look at the tube and my hands. Both ways you are touching. So the normal reaction force is the force applied. There. Normal reaction here. F2 is pushing. F2 is pushing here means touching. So what's the normal reaction force? F2. Here. Normal reaction force is F2. Like. So what are they asking you? What's the friction force acting on the wheel due to each brake pad? So that I'll do here, part D. Friction force equals mu times normal reaction. Mu is given 0.5. Normal reaction is F2. What's the friction force? 60 Newton. How many of you got this? Right there. The normal reaction force acting on the wheel. The normal reaction force acting on the wheel due to the brake pads, due to the brake pads, the normal reaction force acting on the wheels due to the brake pads, that is equal to, that will help us to find the friction force. That will help us to find the friction force. Right. Roman 3. Before brakes are being applied, Roman 3. So this is Roman 2, part A, part B, part C, part D. Roman 3. Before brakes have been applied, this is going at 600 RPM. If the distance to the rotating axis is 5 centimeter, moment of inertia of the wheel is 0.1 kilogram meter squared. Assume that the friction force remains constant. How many rotations take place? Right, there's a loss. So work done by external torque, work energy principle, equals increase in rotational kinetic energy. Work done by resistive torque. Is there any external torque helping? Nothing. Is there increase? No. Loss. Final minus initial, half I omega square. Work done by resistive torque. How many frictions are there? Friction into distance 5 centimeters. That's a torque. Into theta. Work done. Work done is friction into distance is torque. Torque into theta. How many friction forces are there here? 2. 2 friction forces are there. I'll erase this. Okay, no? I'll erase this. If I write in symbols form, symbolic form, frictional torque into theta times 2. Why 2? Here and there, both sides you have. Half I omega squared. Frictional torque is friction into distance. Friction into distance, 5 centimeter. That's your torque. Into theta. Front and back, both there are torques. How many of you all use this equation? People who use the equation? Remember, there is rotation and there is slowing down. So you must consider what? Frictional work done. That means you must apply work energy principle with torque. So work done by external torque equals increase in rotational kinetic energy plus work done by resistive torque. From this, you can get the required answer. Look at the board. Half I omega squared, friction 5 over 100 into theta into 2. Moment of inertia 0.1, omega is 2 pi n, n is 600 divided by 60 squared. Friction we have found 160, sorry. 65 over 100 into theta times 2. They are telling you to take pi as 3. 0.1 divided by 2. Pi as 3. 300 times 2. 600 divided by 100 theta. 0.1 divided by 2. 60 squared. 3600. 6 theta. 6 times 1. 600. 300. Theta is 30 radian. Are they asking the radians or number of rotations? Number of rotations. All of you all know. Number of rotations means what? Theta divided by 2 pi. 30 divided by 2 pi times 3. 5 rotations take place. There you go, full question. How many of you have got 5 rotations? So one shot you have applied and got it. So this is also past paper question. Question number 16 done. Okay, no? Question number 16 done. Okay. Right. So enough for today. Write down the ones who need it. So when you are coming next, please do the or try the MCQs at least and come. At least do MCQ 1 to MCQ 25 and come. You have 50 MCQs, hydrostatics, MCQ 1 to MCQ 25, try and come tomorrow. Yeah. For success students next Friday. MCQ 1 to MCQ 25. Huh? So MCQ 1 to MCQ 25 homework. Okay. Right. Okay, no? Right. Enough for today. Difficult. You don't say. Right, success students. So today, Shakti scores, so your class is completed. Right. Okay then.